So we just said that there is a theorem that tells us that if we start doing a bunch of row operations on a matrix, if we're lucky, we'll end up bumping into a reduced row echelon form matrix. And if all of us collectively started doing random row operations on one matrix, and we all eventually ended up with a reduced row echelon form matrix, we will all get the same reduced row echelon form matrix. This is all good news, but there's still something missing here. In the example we just did previously, we started with a matrix and we just decided, okay, we want to make this thing look like reduced row echelon form, so we just came up with row reductions on the fly. This is not how computers work. Computers need a specific list of instructions to carry out to get from one point to the other. So what we really need is an algorithm that takes us from any matrix to reduced row echelon form. And the Gauss-Jordan algorithm is the exact algorithm we're looking for. So let's walk through the explicit steps here. So if we want to determine the reduced row echelon form of a matrix, we start in the upper left-hand corner. This is where the indices, both I and j, are equal to 1. The first step tells us what to do if the position we're currently looking at is equal to 0. So if we have a 0, then what we do is we look below it for the very first entry that's not 0, and we do a row switch. Now, if there is no entry below the 0 we're looking at, and so meaning that if every entry below our 0 is also equal to 0, so if there is no row switch we can do, we move to the next column and then we start again. So at this stage, if we're looking at a 0, we either do a row switch to get something non-zero, or there is no row switch, so we move to the next column. And then if it's a 0, we do a row switch until we get something non-zero. And so eventually, after we do step 1 as many times as necessary, we are focused on a position where we're looking at a non-zero number. This will become our pivot, but the problem is that we might be focused on a position that is not equal to 1. So now we need to do row scaling by 1 divided by the number we're currently looking at to produce a pivot. Once we have our pivot, we need to make sure that that pivot is in a pivot column, meaning we need to make sure that all of the other entries in that column are equal to 0. So in step 3, we eliminate all non-pivot entries of the jth column, which is the column we're currently looking at, by subtracting suitable multiples of the row where our pivot is. And then we increase I and j by 1, so we move right 1 and down 1, and we start looking for the next pivot again. So after we've processed the last row or last column of the matrix, the matrix is the last stage will give us a matrix that's in reduced row echelon form. So it seems like it's maybe a mouthful here, but really the idea is quite simple. We look for a pivot, scale if necessary, clear everything out. And we keep doing that until we get to reduced row echelon form. So let's see this algorithm in action. Here, we start with a 3x3 matrix, and this matrix is definitely not in reduced row echelon form. Well, what's the problem? So if we start in the upper left-hand corner with I and j equal to 1, we start by looking at a -4. So -4 is not equal to 0, so that's the upshot. We can just immediately go to step 2 of the algorithm. But it's not equal to 1, and in reduced row echelon form, we need 1s for our pivots. So our first step says, well, I'm not satisfied with this -4 as a pivot. I need to scale this entire row by the right number that gets me a 1 here. And the correct number here would be -1/4. So now we scale the entire first row by -1/4. And that produces a pivot in the 1, 1 position. We now have a 1 in the 1, 1 position. So great, we've produced our first pivot, so we're a little bit closer to reduced row echelon form. But again, we're not there yet because we have non-zero entries other than the pivot in this column. So now we need to do row addition to get rid of these non-zero entries in our pivot column. So what we're going to want to do is we're going to want to take the second row, and then we can get a 0 in this 2, 1 position by adding the first row. And then we can take the third row and get a 0 in the 3, 1 position by subtracting off 5 times the first row. So we can do those 2 row additions at once because we're changing rows 2 and 3 independently of one another using row 1, which is not being changed. And when we do those row reductions, we end up with zeros below our first pivot position. And of course, we carry out the arithmetic in those rows. So now we have a legit first pivot column. We have our 1 in the 1, 1 position, and then zeros in the rest of the entries. Great. The algorithm says we're done processing the first pivot position. Now we move right 1 and down 1, and then we repeat the steps. So now we are in step 1, and we're looking at a 0. And so what the algorithm says is look below for the first non-zero entry. But the problem here is that we only have one other 0 below our 0. So there's nothing we can do in this column. We are not going to get a pivot here. This will be a non-pivot column. That's okay. We simply move to the right 1 position. So now we move to the last column and see if we can get a pivot. Well, again, we're looking at a 0, but now we're in luck because we could do a row switch between row 2 and row 3 to move this non-zero entry to our potential pivot position. So that's exactly what we're going to do here. We're going to now switch row 2 with row 3. So when we switch row 2 with row 3, we end up with a 1 in the 2, 3 position. And luckily enough, that 1 will be our pivot. Now, if that 1 were any other number, what we would need to do is we would need to scale the second row by the appropriate number to get a 1 in this position. But we don't need to do any row scaling because we have a 1, which means we'll have a pivot. Great. So now we're a lot closer to reduced row echelon form, except the problem is that we have this pivot, but now we have a 3 above the pivot. So now what we need to do is we need to eliminate that 3 by subtracting off a suitable multiple of row 2 from the row 1. So what we're going to want to do is we're going to want to take row 1 and subtract off 3 times row 2. So we'll take row 1, subtract off 3 times row 2, and send that to the new row 1. And when we do that, we get rid of the upper right-hand corner. This 3 now becomes a 0. And if we look at the matrix for a second, we realize that it's time to stop. We've produced our last pivot position, our last pivot, and there's no more columns to process. So we are now successfully in reduced row echelon form. So we started with this 3 by 3 matrix, which is not in reduced row echelon form. And we went through our algorithm step by step and produced a matrix that is in reduced row echelon form. So the key thing to take away here is that we are following the steps of the algorithm the way a computer would. A computer would simply say, okay, what's the next step? Read it and then do the next step. We're not using any human creativity here. We are blindly following the algorithm. But since the algorithm works, we do end up with a reduced row echelon form matrix.